All right, get ready for an absolute structural masterclass today. We're going to descend straight into the geometric cascade of logos field theory. We're going to explore how a truly profound framework takes incredibly complex, chaotic mathematical spaces and just forces them into an elegant, stabilized equilibrium. If you love seeing how high-level geometry can perfectly dictate pure algebra, you are definitely in for a treat with this explainer. Okay, let's dive into this. At the very top of our cascade, we've got Kakeya tube bounds, specifically spatial volume bounds that restrict exactly how tubes can overlap in geometry. Now, through a highly structured descent, these geometric constraints actually act as a universal stabilizer for unconstrained mathematics. They cascade all the way down to purify one of the most famous problems in arithmetic geometry, the p-adic Birch and Swinnerton-Dyer, or PBSD conjecture. And as a reminder, that's the conjecture relating the arithmetic of elliptic curves to the behavior of their L functions. So here is our roadmap for the explainer today, working our way top down. 1. The geometric stabilizer. 2. Aligning arithmetic polygons. 3. Analytic and algebraic equilibrium. And finally, 4. Purifying the PBSD equation. Now, you might be wondering why we even need this stabilization. Well, in classical, unconstrained mathematics, continuous geometric phases tend to pile up into unipotent caustics. These are infinitely dense clusters of orbits that create uncontrollable singularities and, honestly, just absolute mathematical chaos. Arithmetic slopes fracture into what we call slant poles, and analytic convergence completely collapses. But Theorem 1.2 steps in and applies a Wolff-constrained equilibrium. It forcefully creates maximal saturation, aligns our polygons perfectly, and generates frozen stable invariants right out of all that chaos.
All right, let's start with part 1, the geometric stabilizer.
Now, what's really interesting about this core inequality of Theorem 1.2 is how it bounds the total union volume of unipotent subgroup orbits. By doing that, this equation guarantees that continuous root spaces do not oversaturate localized sectors. It acts as a strict geometric stabilizer, ensuring that our unipotent field components are strictly and safely non-collapsing. Let's unpack these specific variables clearly, because it's absolutely crucial to understand how they translate mathematically into physical geometric actions. The tube map, y of t, sets the unipotent subgroup orbits acting over the local field. But, on its own, it can still cluster. That is exactly where the non-clustering axiom kicks in. It mathematically forbids these unipotent eigenlines from densely piling up in any single sector. Then you multiply this by the delta epsilon factor. That acts as a strict boundary governor mapping to the inverse conductor depth. And boom, the equation actively prohibits the formation of those chaotic unipotent caustics. Moving right along to part 2, aligning arithmetic polygons. To actually shift from spatial geometry over to arithmetic, we essentially need a translator, a dictionary. Notice how the geometric tube scale delta maps directly to the inverse characteristic power, p to the negative f. Simultaneously, the multiplicity count maps exactly to the dimensions of generalized eigenspaces. This mathematical translation is a real game changer. It turns a pure spatial volume bound directly into a strict combinatorial ceiling on the degree of our unipotent operator matrices. Picture a classical, unconstrained system for a second. You get an infinitely sharp slope, a singular collapse where the Newton polygon flares aggressively away from the Hodge baseline. That results in a severe spectral gap defect. But under our new bounds, vertex synchronization forces the limit of the difference between the Newton and Hodge polygons to exactly 0. The Wolff constraints apply a compressed valuation ceiling, totally forcing the Newton polygon to collapse downward and perfectly graze the Hodge polygon at every single vertex. The arithmetic weights identically match the Hodge-Tate weights. Which brings us to part 3, analytic and algebraic equilibrium. Let's walk step by step through the mathematical logic of extracting the geometric dimension of our stabilized space. First, we start by formulating the Minkowski lower hull. In step 2, we take our explicit volume bound from Theorem 1.2 and substitute it directly into the logarithmic scaling equation. Step 3 is really where the magic happens. We resolve the limit as our scale delta approaches absolute 0. The logarithmic terms vanish entirely, leaving us bounded only by epsilon. Finally, taking the supremum over all epsilon greater than 0 proves our Hausdorff dimension is exactly 3. Extracting a Hausdorff dimension of exactly 3? That is incredibly significant. Think of Hausdorff dimension simply as a measure of how densely a shape fills up its surrounding space. A dimension of 3 proves maximum geometric saturation. It means that the exceptional zero variety isn't some thin, sparse fractal set, and it's definitely not an isolated scattering of points. Thanks to our non-clustering symmetries, the zero variety fills the overconvergent weight chambers with absolute maximum capacity.
And this brilliantly illustrates what happens to our geometry. Without this maximum capacity, clustered unipotent paths create singularities that pinch the integration annulus, and that completely collapses the convergence rate. But our non-clustering symmetries keep that annulus wide open. The analytic growth restriction equation shows that the radius of overconvergence, r, stays strictly greater than 1. This bounds the denominators of our power series safely away from 0, mathematically locking in an accelerated, crisp geometric convergence rate. Because of that accelerated convergence, something absolutely beautiful happens to the infinite Fredholm expansion. Normally, this determinant is a highly transcendental, infinite power series that is super prone to boundary anomalies. But our Wolff valuation bounds force the coefficient norms to vanish parabolically. When you combine that with unitary Jaquet integration, the infinite dimensional trace matrix collapses strictly onto a standalone split torus frame. The infinite sum simplifies forcefully and cleanly truncating into an explicit finite Weierstrass product, where we just multiply out exact root factors to a finite degree n.
Finally, we've reached the algebraic bottom of the cascade. Part 4, purifying the PBSD equation. Normally, in unconstrained spaces, clustered caustics force the Iwasawa lambda invariant to exponentially blow up to infinity, creating this endless string of trivial zeros. But our slope stabilization perfectly blocks the expansion of the distinguished polynomial's degree. It entirely prevents that chaotic blowup, strictly freezing the lambda invariant to a constant integer, n-1, and that matches the exact geometric rank of the dual Lie torus perfectly. So, because our vanishing order is firmly locked in, the limit as s approaches 0 of the p-adic L function completely purifies into this exact leading term. The combinatorial invariant scales with absolute linear uniformity. And furthermore, the transcendental p-adic regulator matrix collapses completely into a pure integer lattice discriminant. It totally erases the infinitesimal torsion noise, crushing the Sheffridge-Tate obstruction down to absolute triviality. Pushing this purified equation right to its absolute mathematical boundary brings us to the F1 conformal index limit. Let's break down these limits step by step. First, our multi-scale geometric induction flattens out the non-Archimedean fractal shades as the parameter p approaches 1. In this extreme limit, the PBSD leading term deforms directly into an exact conformal intersection index identity. It proves, definitively, that the geometric sparsity of pure numbers completely regularizes high-dimensional tensor interactions within the Adelic Langlands program. We have just witnessed how a single geometric bound on Kakeya tubes cascades down to tame the infinite dimensional spaces of p-adic analysis, purifying one of math's most complex conjectures into an incredibly stable integer lattice. It leaves us with a fascinating, provocative thought to wrap up on. If geometric sparsity can perfectly regularize the highest dimensions of p-adic analysis, what other chaotic systems in pure math are just waiting for their geometric stabilizer?